In this video I would like to look at diffraction of waves, of course. Firstly we're going to look at a half barrier, so we need to consider our wavefronts approaching a half barrier. This is a half barrier sort of shape or something. This could be water waves approaching a rock jetty or wharf sticking out. I think a wharf is floating, isn't it? I don't know. Or has got room under it for... But this is solid, so the water can't go underneath it. That's the whole idea here. So off the side here, there'll just be reflection. But from the side furthest away, it'll just continue straight across. But what we'll actually find around the edges here is there'll be a certain amount of bending, of water waves bending. So there'll also be a kind of a turning effect going on here. Now, the way I understand this is if you zoom in really close, the wave front is really made up of a whole bunch of little curved wavelets, and as it's travelling in a straight line, you don't really notice them spreading out because there's nowhere for them to spread out. Either they bash into each other and kind of the energy overall bounces back and forth side to side, and overall it just tends to go straight because of those bits. This may be a more helpful way of thinking about it than anything else, than an actual rational argument for it. But when you hit a barrier and you cut it off on the edge, it continues, because it's got that curved edge. The part that if we're looking right up on the edge here is curved, it'll continue to spread out in all directions. But on this side here, since there's other waves travelling across, it has to, the energy can't spread out, it hits into them and just continues straight. So that's the theory there. If you like, you could think of it perhaps as pressure. So there's low pressure on this side and there's higher pressure over here on the wave front, and that would mean that, a little bit like gas expanding into low pressure, the water waves will spread out into low pressure. That means the wavelets here will be of a lower energy than these main ones in the center as well. Okay, so that's a half barrier. Now a full barrier, if we redraw our setup from before, we've got our waves approaching, but this time we've got a barrier on either side. And again, this could be the entrance to a harbour or some artificial reef or anything like that. We tend to talk in water waves, but these also work for sound and for light waves too. But we're going to hit the centre here. The parts on the side are going to reflect back, as we saw before. But coming through, we're going to find them spreading out on both sides. So it'll continue straight here, but there'll be a spread on either side. Keeping the wavelength the same, of course. Wavelength is the same up the top from before and after, and the same down here. The wavelength is still the same, even if I draw them slightly differently. The wavelength is not changing. They're just equal to each other on both sides, but it's spreading out. Okay, so you could have predicted, maybe I should have asked you, and as a prediction, what would have happened with the double barrier or the full barrier, and you get this curved pattern, which is really cool. We're going to make use of this when we start talking about interference as well. So another important detail is that the size of this gap here, the closer that gap size, I'll call that G for gap, so the closer G gets to the wavelength, the maximum diffraction you'll get. Diffraction. I run out of space on the side of my page. So if the gap is very small, you'll get less diffraction, and if the gap is very large, you'll get less diffraction. That's what the textbooks say. I think personally it's just because if we go back up to the top again, how we were talking about these curved wavefronts, you'd assume that's related to the wavelength, those curved wavefronts, or how the energy can spread out. So if you have there might be a link anyway. This is just extension. This is a bit of conjecture, speculation, that the spreading out is related to the size of the wavelength because of the curvature of the wave also being related to the size of the wavelength. That's my thinking anyway. So anyway, that's a full barrier. And now we want to look at radio waves versus light waves really quickly, because this is a common one that comes up in tests. So we've got a hill. It's a hill. And we've got walkie-talkies. Okay, we'll use the walkie-talkies example. And we've got one person here who's talking into the walkie-talkie. Okay, maybe you should draw them more like that. So the signal's going into the walkie-talkie, and it transmits over the hill and is received. And this person here, is their ear. They hear the walkie-talkie. Okay, or when the walkie-talkie is transmitted. Now, you might think, what does this got to do with anything? But what we find is with the radio waves, they somehow bend around the hill, so they curve around the hill or over the hill. But you can't see. So if you're looking at the eyes, you can't actually see the walkie-talkie from the position of this walkie-talkie. So radio waves, which are electromagnetic radiation, the same as visible light is, but visible light waves don't curve round. So the answer to this boggle, because they're both electromagnetic radiation, which means they both should operate and behave the same, and they do actually operate and behave the same, except the radio waves are a much longer or higher wavelength than the visible light rays. Their wavelength is very, very low, low wavelength, high frequency, and the wavelength is too high to bend around the hills. So the visible light travels in straight lines as far as we're concerned, but the invisible light, the electromagnetic radiation in the form of radio waves, can bend around the hill. And it's due to this diffraction idea here, with the gap size or the wavelength size giving it the ability to diffract around there. Very cool.